All right, so 5.3, locating real zeros of polynomials. So when finding zeros of polynomial functions, what kind of zeros can I get? So let me give you some function f of x is equal to x plus 3 times 2x minus 1 times x plus the square root of 2 times x minus 2i and x plus 2i. Okay? So this is the factored form, right? Factored form here. I like the factored form because when we're finding zeros, all we do is we set f of x equal to 0, okay? And then that means we set each of these factors equal to 0 to find the zeros. So let's solve each of these. If I solve this, I have x equal to negative 3. So negative 3, we can have negative 3. Negative 3 is an integer. You could have, if I solve for x here, I get 1/2. So I could have rational. So by the way, both of those are rational, right? Negative 3 is like negative 3 over 1, right? So that could be written as a fraction. Over here, I've got x equals negative square root of 2. So I have rational, but I also have irrational. So irrational, okay, can't write it, represent it as a fraction, square root of 2. This one here, x equals positive 2i, and here this is x equals negative 2i. The I, okay, all of these are real numbers, and the I, these are imaginary. Now, real numbers and imaginary numbers, also known as complex numbers, okay, represented by C, and real numbers represented by this script R here. Okay, so complex numbers and real numbers, those make up all of our numbers that we know. Here, every real number is a complex number. If you think about it, you could write like the number 3 as a complex number by 3 plus 0i. Okay, and then see how that would fall into that set of numbers. All right, so a lot of different types of zeros that we can have. Okay, let's talk about the rational zero theorem. So rational is fractions. So we're not going to be focusing so much on the irrational or the complex numbers here, but rather we're going to spend more time on these types of roots right here. Okay, so the rational root theorem, or rational zero theorem, right? If f of x equals an x to the n plus an minus 1 x to the n minus 1 plus dot 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 all the way down to a1x1 plus a0. And if you put x to 0, that's really x to the 0 is equal to 1. So technically, it's just a0. Okay? So this is just an arbitrary polynomial. Don't get freaked out by this. I mean, I'm basically saying like maybe something like this, 3x squared plus 2x plus 1. Okay? So don't get too scared by that. All right. So if this has integer coefficients, okay? So the example I gave here, all of those are integer coefficients. Then any rational zero of f must be of the form P divided by Q, where P is a factor of A0 and Q is a factor of the AN, okay, the leading coefficient. So the leading coefficient and the constant term, okay, constant and the lead coefficient. These are the important numbers here, okay? So factors of the constant divided by factors of the leading coefficient. All right, so here it is. Possible rational roots. Now you need to understand, we're not saying all the roots, we're just saying these are possible rational roots. Okay, so rational roots, once again, those were the only ones that were rational. You've got other types of roots out there, but we are only focused on rational roots, okay? And this is a list of possible roots. It doesn't say that every one of these are roots. It just says that these are possible candidates. Every one of them could be not a root, okay? So, but it's possible. So I have a factor of constant term divided by factor of lead term, okay? So I just want to note, this does not necessarily find even a single zero. So this could be a complete dud, okay? It only identifies a list of potential rational numbers that could be zeros. Okay? Only a potential list of numbers that could be zeros. So we must test each of the zeros by using synthetic division, right? To see if they are actual zeros, and then we go on from there. Okay? So this tells us nothing about irrational zeros or imaginary zeros, only about things that are rational zeros. Okay? So just to give you an example, here's your example. List all possible rational zeros of f of x equals negative x to the fourth plus 3x squared plus 4. Okay? Now, what do I know? My two important numbers here are the lead coefficient and the constant. So the constant term, this is equal to 4. The lead coefficient, this is equal to, well, it's understood if there's no number in front, it's understood to be a 1, so that's a negative 1. Okay? Now I think about this. What are factors of 4? Well, if I multiply 1 times 4, I can get 4. Okay? Also, if I multiply 2 times 2, I can get 4. So 1, 2, and 4, those are factors of the constant term. Now, not only can I multiply 2 times 2 to get 4, I can also multiply -2 times -2. So not only is it the positive ones, but I also have all the negative ones. So how we write this shortcut way, instead of writing out -1, +1, -2, +2, -4, +4, I put 1, 2, 4 in parentheses, and then I put this plus minus on the outside. Okay, and so that kind of shortens it up a little bit for us. Okay, now down low, the factors for -1, well, my gosh, that's just 1 and -1, right? So it's kind of silly to write out 1 and then plus or minus 1, but you can if you want. If you want to do that, that's fine, just to be consistent. Now, what does our rule say? It says the possible roots are what? The constant divided by the lead term. Now, how you remember that, divided by the lead term, that's up to you. So this is my A0 over my AN. The way I remember it, okay, I remember it like this. I think of, say I've got this function like, I don't know, 4x to the 5 plus 2x squared minus 11, okay? Which term is the most powerful? Well, the most powerful one is x to the 5th, right? Okay, what's the least powerful term? That's the 11. I kind of think of this, I know this is goofy, okay? This is the big guy on the block, right? And then this one's not too big, and then that one's the littlest. I kind of think of it like a tree, okay? I kind of think of this like a tree. So where's a tree big? It's big at the base, 4x to the 5th. And then as we go up the tree, it gets skinnier and skinnier, less and less strong. Okay, and then we get all the way up to the top. It's easy to break off limbs up at the top, right? So then it's like, oh, this one divided by this one. So that's kind of how I think about it. Now, that's kind of silly, you know, and like I said, I'm silly, and that's a silly way to remember it. No mathematics behind this whole tree thing. Another thing that some students have told me that they think of is they see a constant over the lead, that AO over AN. This is like on. So I don't know. If it were me, I might get it confused with no. But if you understand that on top, yeah, that'll work. You know, however you want to memorize that, it's the constant divided by the lead term. The little guy over the big guy. Okay, big guy's on bottom, little guy's on top. All right, maybe, however you want to remember that, I don't care. Okay, so what's the constants? Well, those are factors from 1, 2, and 4, plus or minus. And then in the denominator, it's plus or minus 1, right? For the lead term. So we need to do all the pairs of this, okay? So what are all the pairs of this? Well, I have a 1 paired with 1. So that's 1 over 1, plus or minus, right? And then I have a 2 paired with the 1. So that's 2 over 1, plus or minus. And then I have a 4 paired with a 1. So that's 4 over 1, plus or minus. Now those over 1s, those all reduce. And so I just get plus or minus. And what do I have inside my parentheses? 1, 2, and 4. Okay, and close my parentheses. So all it says is to list out all possible rational roots. Now in your homework, it might have something like this. It has a plus or minus and then a curly bracket, and then you just put in the numbers 1, 2, and 4. But if it doesn't, you might have to type out 1, -1, 2, -2, 4 comma negative 4, okay? And so that would take care of all possible rational roots. Now those are possible ones. It doesn't necessarily mean that they are all roots or zeros. So be careful with that. All right, good luck.